You're probably wondering who we are if this is your first time. We're Black Hills Information Security. We do these webcasts quite often, and we do it because it brings us joy. Like really, that is why we do it. We like to share our knowledge with people. We, in fact, hire people who like to share their knowledge. Like it starts at the hiring process of, hey, do you like to share your knowledge? Do you want to, do this? Do you want to make webcasts? Do you want to do blogs? And if those people are like, yeah, I do. And I was like, all right, cool. Come join us. So Kyle is one of those people who likes to share his knowledge, and he's going to share his knowledge today in this 1 hour webcast. So during the webcast, if you have questions, feel free to ask them inside GoToWebinar or Discord. If you want your questions to be answered quicker, then ask in Discord, because there's hundreds of people there that can answer it. If you ask inside GoToWebinar, there's like 2 of us. And so it's a lot easier for your question to be answered inside Discord. And with that, Kyle, I'm going to turn it over to you. You have a 4.82 rider rating at Uber. I don't know what happened, but it is all yours today. Take it, Kyle.
Like we've said a couple times, my name is Kyle Avery. I do have a 4.82 Uber rating. I'm also a pen tester and a developer with Black Hills, and I'm an instructor with Wild West Hack and Fest. I put my Twitter and GitHub there, so feel free to follow those. As far as what we're going to talk about today, so we're going to start off just talking about what exactly is .NET and why we should care. And then we'll go into how exactly we can execute .NET programs in a way that is sort of hard to detect. And then we'll move to talk about AMC and ETW, which are the primary log sources for .NET. After that, we'll talk about obfuscating .NET assemblies to get around those logs. And finally, we'll go over what I refer to as Operation Prechecks. So first off, we'll just move right to Intro to .NET. So what exactly is .NET? So this is something from Microsoft that is basically a library that can be used to build new programming languages off of. And that's sort of a crude definition, but essentially it is this large API that can be used as the foundation of a programming language to provide it with basically a bunch of boilerplate features so that you don't have to add those in yourself. So probably the most famous .NET languages are C# and PowerShell, but there's also F# from Microsoft. There is some open source implementations such as Iron Python and Booleang that have some popularity in certain areas. But today we're going to be talking mostly about C#. And so .NET and C# are not the same thing. They are somewhat interchangeable depending on the context. I'm probably going to mistakenly use them interchangeably when I shouldn't. But just know that .NET is sort of the library that C# is built on. C# is the actual language that we're talking about. So the .NET framework is specifically what we're talking about. And the .NET framework is the Microsoft Windows implementation. It's closed source, and it only runs on Windows. There's a newer sort of implementation of this called .NET Core that we're not going to really go over today. It is cross-platform, it's open source, and it will also run sometimes unmodified, sometimes slightly modified .NET framework tools. But again, that's not something we're going to go into today. If it's still not making a ton of sense, one thing that I sort of heard early on that helped me understand it, and I guess coming from a university background where we did a lot of Java and things like that, is that the .NET runtime for C# is a lot like the JVM for Java. It's this sort of interpreter that sits between the machine and your sort of intermediate language code, which in .NET is referred to as Common Intermediate Language, CIL. In Java, it's referred to as Java bytecode. So it sort of sits in the middle and must be installed in order to interpret that .NET assembly, as it's called. So this runtime that I keep referring to is formally called the Common Language Runtime, or the CLR. And one thing to note is that the CLR major version installed on an endpoint must match the major version of the software that you want to run. So if you build something for, say, .NET 4.5, the target endpoint must have .NET 4. something installed. It could be 4.0, it could be 4.8, but as long as it has a matching major version, it should run. And so when you think about this, it becomes clear that you need to sort of know a little bit about the endpoint that you're planning to execute code on in order to, have a successful payload, right? But luckily, we can sort of generalize and assume that Windows 7 and Server 2008 era is going to have .NET 3. something installed, and Windows 10 and Server 2012 and newer are going to have .NET 4.0 or 4. something installed, rather. The other thing is that .NET Framework projects are backwards compatible at build time. So if you write something for .NET 3.5, you can typically build it for 4.5. It doesn't always work the other way around. But once you've built that .NET assembly, that will only run with the major version. Even if you build it for 3.5, it will not run on a host that has 4.5 installed. Technically, you can install multiple framework runtimes on a host. So you could install .NET 3.5 on Windows 10, and then you could run either program. But by default, Windows 7 is only going to have .NET 3.5, and then Windows 10 is only going to have .NET 4.5. Someone asked, how easy is it to port .NET from a Mac? So that's where you either have to look at something like .NET Core, or there's also an open source project called Mono, which is sort of meant for running, I believe, for running any .NET program. I'm not totally sure, but yeah. So typically we're going to be looking at mostly Windows exclusive things, but porting something, especially porting it from .NET Framework to .NET Core, is typically not that difficult. But it really just depends on what sort of libraries the project is using and whether or not those have been ported to the new version. So just a couple of key features that sort of matter to us as offensive security professionals. First of all, .NET has the ability to load other .NET programs dynamically. So the .NET library has a method assembly.load, which we're going to be talking about a lot today, that can essentially be used to load an arbitrary .NET assembly at runtime. So you can pass it as an argument or as data or whatever you want to that method, and it will execute it without it having to be included in the original file. So you can see for post-exploitation, this is particularly useful, right? Because we can provide payloads or tools to our implant, and it will execute them without them having to be included in the initial malware. There's also the .NET API, which I've kind of talked about a little bit, but this is nice from a speed of development perspective. From the .NET API, it gives us access to Windows components such as WMI and even COM. It gives us access to Active Directory with LDAP queries, and even like networking boilerplate code, and basically just saves us a lot of time having to write out a lot of different, I guess just boilerplate code at that point. Or you're just writing implementations for things that you're probably going to get from some other library anyway, and now you can kind of skip that because the .NET library has already sort of set that up for you. There's also pinvoke. So one thing you might be wondering if you're coming from an unmanaged or a native language such as C or C++, is, how do I call something like virtual alloc or write process memory? And that's where pinvoke or platform invoke comes in. And that is a feature of the .NET API that allows you to call functions from unmanaged libraries. So you can load an arbitrary unmanaged DLL and then call functions that are exported from it. And then finally, something that I think is particularly useful is the ini CPU platform target. So what's nice about this is that you can output one file and it will target x64 and x86 computers. And this is sort of interesting. The way that it essentially works is the binary is, or rather the .NET assembly is set up so that it can instruct the .NET runtime to sort of figure out which architecture it should be running as, and then sort of fix all of the things that need to be handled in terms of architecture. And so the default for this is that it will actually try and prefer 32-bit. That's a checkbox that you can change and can cause some problems for you depending on how low level of things you're trying to do. But it's definitely a convenience that you can just build one output file and use it for both. So why do we care as offensive security professionals? So beyond those features, right, from all those features were specific to .NET. So why do we care about C#? Well, years ago now, PowerShell was sort of the de facto language for post-exploitation, because not only did it have all the features that I've already discussed, but you could also provide plain text scripts instead of binaries. And so you could edit things more quickly. You could, it was just a faster language to use than something that you have to build every time. But with PowerShell 3.0 introducing the commandlet logging, and then 4.0 and 5.0 introducing AMC and script block logging and transcript logging, all of these different features have been included into PowerShell as language features to make it more difficult to execute them. Not impossible. There are still many groups and teams using PowerShell successfully, but it's definitely more difficult. And so the industry, overall, has sort of moved away. One thing that was asked is do red teamers tend to install .NET on their targets to make sure payloads work? I personally don't think that would be a good idea. You typically don't want to install anything if you can help it, right? And you may not even have the right privileges to do that. The nice thing about writing .NET Framework payloads is that if I build a payload for .NET 4.5, I'm pretty confident that it's going to run on any Windows 10 or Server 2012 and up machine. And if I build something for .NET 3.5, I'm pretty confident that it will run on any Windows 7 or Server 2008 machine. So there's really no need to bring the .NET Framework with me. I can just run it using the existing .NET runtime on the host. So back to PowerShell, though, when all of these protections were coming out as language features, C# was sort of the natural next step. It's the second most popular, or maybe the most popular, depending on who you ask, .NET language besides PowerShell. It has that built-in assembly.load method, so we can still use it dynamically, similar to how we were using PowerShell. And it has a lot of the same features. And so it's easy to sort of port things from PowerShell to C# because a lot of the language syntax is similar, and there's a lot of features that sort of match up. And so ever since this idea came out, there have been many different post-exploitation tools written in C# popping up on GitHub. So started, I believe, with SpectreOps. They put out the Sharp pack, which includes Rubius and Seatbelt and a bunch of other tools that you've probably used. And now there are tons of tools on GitHub. There's the Sharp collection from BlankVic, which sort of documents these and also gives you built assemblies. And so being able to use .NET assemblies in your post-exploitation tradecraft is really important, or else you're going to miss out on all these new tools that are coming out, and you're going to be kind of stuck with the PowerShell tools that have overall kind of slowed development in terms of offensive security. So with that, let's move to methods of execution. So Metasploit, Cobalt Strike, and pretty much any usable C2 framework these days has a command built in to execute .NET assemblies or build C# projects really on an endpoint completely in memory. So the way that it works with Cobalt Strike is that it is going to spawn a new process. It will be a child process of your beacon by default. It will inject a reflective DLL into that process, which will load the .NET runtime. And then that DLL will also load an intermediate .NET assembly, which sort of handles the output to send it back to the beacon and also any errors to try and keep it from crashing. And then finally, that intermediate assembly will load the assembly you provided, and then we'll just execute the entry point with any arguments that you pass to it. So this communicates back to your beacon using named pipes, or excuse me, unnamed pipes rather. Some features of Cobalt Strike use named pipes, some use unnamed pipes. This is one of them that uses unnamed pipes. So in case you aren't familiar, I just recorded a quick video of me running execute assembly so you can sort of see what this looks like. So you can see it might be kind of small. I don't know how to make Cobalt Strike any bigger. So I'm just running execute assembly. I'm passing it seatbelt.exe, which is an enumeration tool that we're going to be using today. And then I'll give it the OS info argument. It will upload that to the beacon as a byte array, and then we'll execute it in that child process. So you can see I get some information about the endpoint, and it didn't write seatbelt to disk anywhere. Nothing else was put on the system. It was just executed in memory. This process is sort of commonly referred to as fork and run. And so fork and run, there's a few considerations we need to make to ensure that this doesn't get detected. It used to be when fork and run first came out that it was really difficult to detect because security tools weren't really looking for it. But now, since Cobalt Strike and so many other frameworks use this so heavily, and there are many security tools, specifically EDR products, that are like very heavily looking for fork and run behavior. So first of all, the host for your .NET assembly, so that child process that we're going to spawn, needs to be a plausible child process with legitimate looking command line arguments, right? So the default configuration for Cobalt Strike is to launch run DLL32 with no arguments, which is super unlikely. Run DLL32, if you open your command prompt on your Windows computer and run that, it will immediately exit. It will not do anything because you did not provide it a DLL to run. And so seeing a process called run DLL32 just persisting for a long time while your tool runs, or for any amount of time really, very suspicious and typically caught very quickly. And run DLL32 is also just not a child process of everything. And so if you have some process that your beacon is living in that wouldn't have run DLL32 as a child, that's also going to be pretty suspicious. Luckily, you can define this child process in your malleable C2 profile. So you've got the spawn2, x64, and x86 that will define for each architecture which process spawn. And you can actually provide, if you give it quotes, You can provide full command line arguments to that as well. You can change this at runtime as well. So in Cobalt Strike, you can type spawn to, and then space, and then whatever architecture you want, and then the name of the process you'd like to spawn. And you can sort of change this as you're operating. The other thing that's really useful is Cobalt Strike has a PPID command to actually change what the parent process of this will be. And so this sort of opens up a lot more options for parent process or parent-child process relationships, because now you can implement a spawn to process that is a child of some totally unrelated process to your beacon, and make sure that that's a common relationship, and then execute your payloads that way. So I included this graphic. I know it's cropped because it's a huge graphic, so I put the link there that you can find later. But I grabbed this from Twitter not too long ago, and it's meant for network defenders, I think, typically. But what this is to show you is like what the normal child-parent relationships look like. So you can sort of see what the parents and what the children are of each of these common processes that run. And so this is, I think, a really good guide for sort of picking your spawn to processes, at least from the perspective of a legitimate parent-child relationship. And then once you've picked this, I recommend you just open up something like Process Explorer or Process Hacker, wait for this relationship to form, and then look to see if they have any, arguments in the command line, because that's also very important. One thing that I've sort of noticed, and I don't know if this is actually true or not, but it's just something that I've been experiencing lately, is that EDR tends to be focusing less on process relationships. They're still definitely checking for that, don't get me wrong, but as far as fork and run goes, I've had less scrutiny on the child processes that I choose, and more scrutiny on abnormal .NET runtime loads. So when you kick off a fork and run instance, the subprocess has to load the .NET runtime DLLs from disk so that it has all of the necessary components to execute your payload. And if you load something that never loads the .NET runtime, then that's going to be very suspicious. And there are lots of ways to collect image load events. So sysmon will collect image loads. And so there's all of these different executables that you might be using that aren't typically going to load the CLR, and now they are. We've got a question: can we implement sleep technique to improve our tradecraft within fork and run? Yeah, so I'm going to talk about some of the different Cobalt Strike, it's like, I guess, the reflective DLL options for memory obfuscation here in a second. So I'll get to that in just a minute. So as far as finding a spawn to process that typically loads the CLR, there's a couple ways that we can do this. Outflank, not too long ago, put out a Cobalt Strike beacon object file, a BOF, called find objects. And find objects is nice because you can essentially run this in your process. There's no child processes, there's no reflective DLL injection, nothing like that. Find objects BOF will look at each process that's currently running to see if it's loading whatever DLL you specify. So you can call find objects BOF and look for anything that's loading the CLR, or CLR.dll rather. And this is actually really effective because it can help you find spawn to targets that are specific to the target environment, not just general Windows utilities. Beyond that, you can also use something like Process Explorer, or I mentioned earlier, sysmon, on your machine, totally off endpoint, to just search for processes that have a handle on CLR with Process Explorer, or watch for image loads with sysmon. So I've got a couple examples here. On the left, you can see Process Explorer. I'm just searching for CLR.dll, and here's a couple processes that are running it. Some are malicious, some are not. On the right, you can see I'm running find module, which is part of the find objects BOF project, and I'm looking for CLR.dll. And again, I can see all of these different processes that are running the .NET runtime. So with that, to answer this question now, so one feature of EDR that's very common is it will also be scanning sort of the memory of processes for suspicious data or page permissions, right? So this is why you typically hear that you want to avoid something like RWX memory, right? Because it's very uncommon for processes to have read, write, execute memory. Somebody asked if I would recommend Cobalt's execute assembly or a customized manner. That's actually a really good question. I find that Cobalt Strike's execute assembly is still very usable if you take the proper precautions. There are alternatives. I didn't mention any of them in this presentation originally, but there's one in particular called execute assembly, like all one word with a capital E and a capital A. That's a really good example of implementing some improvements into the project that you might be interested in checking out. So As far as Cobalt Strike goes, though, like I said, there are ways that you can configure it to be a very viable option. So to sort of avoid these memory scanning things beyond just typical process injection considerations that we use for something like shellcode injection, in this particular case, we're worried about typically that reflective DLL that's being loaded by Cobalt Strike into the process. And so Dom Chell from MDSec put out a really cool tool called Sniper that's not really meant for finding the reflective DLL portion. It's meant for finding the .NET assembly portion, which we'll talk about a little bit later. But Sniper tells us how this tool and probably EDR is looking for PEs in memory, right? So basically what he's doing is he scans every page that is tagged, I believe, read execute or read write execute, and he looks for the exact bytes that match a PE header. And so this is very telling to us right now. We know that we should be changing that value. So fortunately, there is a repository from Joe Vest who works at Cobalt Strike called Malleable C2, and he basically documents how all of the different options work in the profile. So he has example profiles with comments. And some of the options that I think are really important for obfuscating this reflective DLL. First of all, prepend, so you can add some random bytes to the beginning of your reflective DLL, which would ruin that signature tool that Dom Chell wrote if it was sort of looking for this, right? You can also use string replace to replace certain strings. So you could replace the reflective loader method name, you can replace beacon.dll, you can replace all these different things in your library that is loaded, right? You can change the MZ and PE header values with magic MZ and magic PE to be different values, so that makes it a little bit more difficult to find as well. The obfuscate setting is really interesting actually, because it does a ton of different things. So it will obfuscate all of the imports. It will actually overwrite a bunch of header information. They don't really document this super clearly what it does, but that's sort of their explanation of what it's doing. Smart inject is an interesting option because it will sort of remove get proc address and load library from the import address table entirely and sort of embed what they're referring to as function pointers directly so that it doesn't have to resolve those in the traditional way. You can set use RWX to false to avoid RWX permissions whenever possible. And then finally, you can set cleanup to true, which will release any memory associated with that reflective DLL after your payload has finished executing. So just to give you a quick example of what that kind of looks like, you can see I'm setting use RWX to false, I'm setting obfuscate, cleanup, and smart inject to true. I'm setting some different MZ and PE header values. And then finally, for x86 and x64 specifically, you can set options such as prepend or string replace. So you can replace things with another string, such as reflective loader being replaced with the word kickoff here. You can replace strings with nothing, such as this program cannot be run in DOS mode being replaced with just an empty string. And you can also add strings. That's another option that they offer. I'm not totally sure why you'd want to do that, maybe to confuse analysts or something. But typically, I'm just going to use prepend and string replace to, I guess, just replace and remove different strings. So back to the sort of sniper tool that Dom Chell wrote, what he's specifically looking for is not the PE header of the reflective DLL, but the PE header of the .NET assembly. So the reflective DLL is injected. It has all the code to load the CLR and then load the assembly, but it has to load that .NET assembly into memory as well. So now your entire .NET assembly binary is loaded into memory, and that also has a PE header. And so one thing you can do to sort of get around this, Dom Chell, again, with his sniper tool, he put out this sort of snippet that you can use that will, at runtime, erase the PE header. So this is something you would have to add to the beginning of a C# tool that you want to use, and we'll talk about automating that towards the end of the presentation, at least a little bit. But you can use this to sort of overwrite the first X bytes in your region of memory so that it doesn't have that PE header anymore. So just to go over some kind of alternatives to execute assembly, I already mentioned that other project that's also called execute assembly, which is just an alternative that uses fork and run, and it will also provide some other features such as bypassing ATW, and then it will overwrite the PE header for you. But there's also ways to execute .NET code without using fork and run. So I think the most common variation that I see is actually taking some position independent shellcode that has your target .NET assembly, and then at the beginning of it is prepended with a stub that instantiates the .NET runtime. And so this is great because you can basically use any traditional .NET assembly, or excuse me, any traditional shellcode injection technique to get this to execute now. And you can inject it into already running processes, which is pretty interesting. And so you're probably wondering, okay, that's great, but how do I get this position independent shellcode with a CLR stub at the beginning? Because I have no idea how to write assembly. And I also would not know how to write this assembly from scratch, right? But luckily, there's a tool called Donut from the Wover and ModXP. And what this will do is it will generate that shellcode for you. You provided a VB script, a JScript, an unmanaged Exer DLL, or a .NET assembly, and it will convert that to shellcode. This is great because it doesn't have that reflective DLL. So you're removing one step that you have to worry about entirely, like you do with fork and run. The one problem with Donut is that it will allocate at least one region of RWX memory, if not multiple, if you select certain bypasses and things that it has built in. So that's definitely something to sort of keep in mind. Now, at the same time that Donut came out, Accenture put a tool out called CLR Avoidance, which is very similar. It does approximately the same core functionality. The sort of benefits to it are that it does not need to allocate any RWX memory whatsoever, unless you specify for it to at build time. And it also has this sort of APC safe shellcode generation method that will basically preserve the register so that it doesn't mess up any other threads if you perform an APC-based injection method. There are a few disadvantages to CLR Avoidance, though. First of all, the shellcode is going to be larger than the Donuts would have been. The Donut shellcode is much larger than CLR Avoidance if all the defaults are used for both. But if you use Donut and you remove the options for bypassing and for compression and all these other things, it's going to be smaller than CLR Avoidance would have been. There's also no ways to pass arguments to your assembly in CLR Avoidance. So one nice thing about Donut is you can use the, I believe, TACP flag, and you can pass it arguments at shellcode generation time. CLR Avoidance doesn't have any of the built-in bypasses, such as AMC bypass, or even payload staging that Donut does. And CLR Avoidance will only take .NET assemblies. You can't give it VB script or JScript or unmanaged executables. So that's another kind of interesting bit. Now, just last night, I posted this tool on my GitHub. It's called Third Eye, and it is just a wrapper around CLR Avoidance that allows you to pass arguments. And what it's going to do with those is it actually has an intermediate .NET assembly that it will hardcode those into. It will load the .NET assembly that you're targeting, such as Seatbelt, as a resource, and then it will build that wrapper payload, and it will generate shellcode from that. You can encode the shellcode with SGN as part of the tool as well, and that's a really good shellcode encoder that I've had, good luck with. But the problem with that is that then you do have to use RWX memory, at least initially, while SGN is running. So that's sort of a consideration that you can make as well. But yeah, so I've got a quick demo of Third Eye here. So you can see I'm going to run Python. I'll specify the architecture, which it's going to default to 64-bit, but I specify just in case. And then I pass it OS info and Seatbelt. I'll then convert it to base64 and write that to a text file. I'm going to go ahead and read that text file. And it's just going to have a bunch of random data because that's the base64 encoded of the shellcode. I've included the Donut test shellcode runner as part of the project to make testing shellcode easier. So I'll copy that payload to my virtual machine, and then I'll go ahead and run that. And you can see Seatbelt executes and runs payload. So all that to say that Third Eye basically allows you to pass arguments to CLR Avoidance and use it in a way similar to how you would use Donut previously. All right, so now we can move on to .NET log sources. So assuming that all of that, let me go back. So assuming that you found a way to securely run any payload with fork and run. So you've set your Cobalt Strike profile up, you found a plausible parent-child relationship that loads the CLR. Assuming all of that is set up, or you've decided to go with some kind of shellcode execution method, now you have to worry about logs that are included in the .NET runtime. So anytime a .NET payload is ran, there are log sources, specifically AMC and ETW, that we're going to talk about, that are included in the CLR that we need to also be concerned with. So first of all, AMC. So the anti-malware scan interface is this component of Windows. It initially came out, I believe, as a way for as a way to scan PowerShell scripts at runtime, but it can also be used for many other things. Macros are subject to it, even XLM macros now. And in .NET 4.8, it will scan certain methods that are run, and specifically assembly.load, which is the primary method used to execute .NET assemblies dynamically, is going to be scanned by AMC. So there are a couple ways to get around this. First of all, we can patch AMC. AMC is a DLL that's loaded into our process. There's a method called AMC scan buffer, and you could potentially overwrite that with new bytes. But I found that that's sort of an indicator itself. There are multiple EDR now. I know F-Secure does, I know CrowdStrike does, that specifically look for AMC bypasses by scanning DLLs such as AMC in memory and comparing them to the one on disk to see if they've changed at all, because it really never should. So in reality, you can bypass this just with sufficient obfuscation. AMC, at the end of the day, is a strings detection mechanism. It's looking at, 4 signature bytes. And so if you can obfuscate your assembly, you shouldn't have to worry about AMC scanning. Now, there is a case of some security products using custom AMC providers. So Carbon Black does this, Sentinel-1 does this. I'm sure many others do. I don't know off the top of my head. And what this is going to do is they will actually write their own AMC.dll, which has an AMC scan buffer function exported that, when loaded, will send it to some other totally different scanning mechanism. It might be some cloud-based, it might be some totally different strings list than what Microsoft uses. Whatever it is, they're doing it differently. And this is difficult to test locally, right? With traditional AMC, we can test payloads against the AMC installed on any Windows machine, and it should produce the same results. Whereas this, we don't have access to that custom AMC DLL. Fortunately, at least so far, I haven't seen any practical difference. Any payloads that I've had that bypass AMC locally have also bypassed custom AMC providers. So at least right now, I don't think this is really a huge obstacle, but it is something to keep in mind. One thing you could do if you are particularly worried about this is there's a project from Path to File. It's called Simple AMC Provider. And this is an example of making a custom AMC provider. And I don't remember exactly what his does, but it might already do this, or you might have to modify it. But you can have it just write every piece of data that's sent to AMC to a file. And that way you could look at what exactly is AMC even seeing, what pieces of my payload is it getting, and are there things in there that I think could be indicators, right? So beyond AMC, there's also ETW, and this is sort of, in my opinion, the more difficult to get around logging source in .NET. Oh, let's see, I got a question. Any research to help folks get enough background understand? So honestly, somebody asked like how I kind of got started with C# and how you might sort of learn more about it. So C# is one of those things that is nice because there are now lots of resources online. So one thing that I always recommend, there's a project from Ryan Cobb at SpectreOps called Sharpsploit, and it is a library written in C# of a bunch of different .NET post-exploitation and, I believe, initial compromise payloads. So he writes examples for many different initial access and lateral movement and bypass techniques, right? And he writes them all in C# as standalone files, pretty much. And you can use that as sort of a reference to sort of get started. And really from there, I think the best way to learn is by taking tools that you already want to use, something like Seatbelt or any other of the SharpPack tools or any other of the Sharp collection tools, taking those, looking at them to figure out, what exactly is it doing and how might it get detected and how might I modify it. And basically just playing with open source tools as a start, and then maybe moving into writing your own things, whether it be from scratch or just kind of piecing together pieces of other tools to do something unique, is kind of at least how I got into it. As far as Python, honestly, I don't have a ton of Python experience. Third Eye is written in Python, but it's a relatively simple script. And it's something that I just sort of piece together with the Python knowledge that I have, I guess. All right, so back to ETW. Sorry for that little detour. So ETW is a kernel mode feature for system logging. And when you hear that, you might think, oh, then I shouldn't be able to bypass it in a process, right? It's not like AMC where a DLL is going to be loaded. But fortunately, that is incorrect because the Microsoft Windows .NET runtime provider actually sends logs from the .NET runtime to any subscribers to that provider. So what this means is that we can bypass ETW in process if we want, in a very similar way to how you would bypass AMC. ETW is interesting because it's not strictly a strings detection at all. Microsoft has no bad or good list. What it actually has is just the ability to detect any .NET method names, class names, namespace names, the assembly info. It'll take all of that and just send it as JSON logs, essentially, to anyone who's listening, really. So your EDR could be listening, any antivirus, anything that's on your system could be listening for those logs. And it will collect, any class names and method names. And so you can imagine if I execute Seatbelt, it has Seatbelt as the namespace. The class name is Seatbelt. That's going to be in there, very obvious. Maybe a better example would be if I ran the Bloodhound collector, it's going to have Sharphound 3 in the name, which is almost certainly a malicious program, right? There's not very many other people that are naming their things Sharphound 3. So there are some other sort of methods, even if you were to change all of those, right? So if I use something like compile assembly from source or assembly.load, this could be flagged by ETW for dynamic code execution, and that's not something that you can easily change. You could also combine something like from base64 string and pinvoke calls such as virtual-alloc and create thread to look for shellcode execution without necessarily being able to obfuscate those very easily as well. Back to my sort of argument about whether or not you should bypass it, security vendors are looking for ETW bypasses. And so if you can avoid that, I think it's better to just obfuscate your payload as opposed to bypassing ETW. So going into .NET obfuscation, right? This is how, at least at Black Hills, or at least in my operation, I don't know how everyone here operates, but I personally don't perform any AMC or ETW bypasses when I'm using .NET assemblies. I exclusively rely on .NET obfuscation. And this is something that has worked really well for me so far. So once we found our fork and run execution method configuration, we're going to move to .NET specific logs, right? We talked about AMC and ETW. These both need to be either bypassed or evaded. AMC is one of those things we can test offline if we want to by, running it against the AMC provider on our host, unless they have a custom provider, in which case it's going to be different. Kind of like I said already, you often don't need to bypass these protections. You can just obfuscate your payloads. This is easy to test against AMC because we can just see if it bypasses or not. It's a little bit more difficult for ETW or custom AMC providers because we don't know what the EDR or security products are doing with that data. And there are some scenarios where we can't necessarily obfuscate things. So pinvoke or some of the assembly.load methods can't necessarily be changed. There is a project that we're not going to have time to talk about today called DNvoke from the Wover as well, where you're actually dynamically resolving the functions that pinvoke would be loading. And so I think the initial reason for them creating this was to avoid things being in the import table, but it could also be used to replace something like virtual-alloc and name it really anything you wanted. But this is going to introduce a bunch of boilerplate code that now you have to worry about that being signatured. So it's kind of brings some pros and cons as well. Let me ask, does an EDR override AMC protection? EDR will not, so EDR does not typically override antivirus or any components of it. Theoretically, you could have a different antivirus installed that would replace Defender, and that in which case you may not have AMC active. Although I think these days most antivirus and most EDR, at least the reputable ones, are all going to be using AMC because it's free and it's well documented. And I think for a while there was sort of like some public outcry of why vendors weren't using AMC since it was already provided to them. So I think it's pretty common to find that EDR and custom antivirus are all going to be using AMC. So that's something that I assume is going to be on and enabled every time. It may not be every time, but I'm just assuming it is because it's easier to sort of err on the side of caution, right? So let's talk about obfuscation. The most popular open source way of obfuscating things is probably ConfuserEX. This is something that MDSec has talked about using, SpectreOp has talked about using. We used to use this for a long time. And ConfuserEX is great because it's totally free. They've got a GUI as well as a command line version of this. And what both of these do is they'll load an XML template. You can see an example here, and they'll use that to obfuscate assemblies. So in this template, I'm setting, first of all, the preset to be normal, which runs basically every check that they have. And then I'm removing a couple things. So I remove the watermark, which is a sort of tag that it puts in the header that says that it was confused by ConfuserEX, which I obviously don't want. And then I also removed control flow and reference proxy obfuscation, which you might be wondering why. Those do work well, and they actually are sort of useful in sort of adding proxy methods and changing how the layout of the process runs. The problem with them is that they do increase the size of the binary quite a bit. And so for something like Seatbelt that's already kind of large, it's going to go over 1 megabyte typically. And one thing that I didn't mention earlier is that fork and run with Cobalt Strike has this sort of undocumented soft limit of around 1 megabyte. And so if you have payloads that are, above 950 kilobyte, they're probably not going to run with execute assembly. And so I err on the side of caution, and I just remove these for any payloads that are anywhere near that sort of 900 kilobyte, range. So that's why I have those there. So just to show you real quick, I'm going to go ahead and obfuscate Seatbelt, which is kind of the tool I'm using for everything today. So I've got the rule there. It's the same one from the presentation. I'm going to load that project. I'm going to give it the desktop as the base directory. And then I'm going to go ahead and run protect. It will add all the protections to Seatbelt. Then I'll have a new directory confused on my desktop, and you can see Seatbelt there. It's only 759 kilobyte, I guess. So that's well within the bounds of Cobalt Strike, but now it's going to be totally obfuscated. There are a couple things that ConfuserEX, at least with that normal preset, will not obfuscate. And these are actually really important because they're things that Yara rules are commonly looking for in executables. So on the left is a screenshot there from the Seatbelt GitHub page. I went to the csproj file of Seatbelt, and you can see there's a GUID, and there's also an assembly name. And the GUID and the assembly name are definitely signatured. And on the right, this is a view of the Seatbelt.NET assembly that I obfuscated with ConfuserEX in that demo video. So you can see it still has the title Seatbelt, it still has the same GUID. And so those are things that we absolutely need to change if we're going to successfully execute these on a host. So just to give you an example of how people are detecting these are actually the rules that FireEye released when their toolset was potentially compromised. And they basically just gave you the GUID, and in some cases gave you maybe a couple bytes, but for both of these, they just give you the GUID and the condition that it must be APE file. So changing that is obviously very important to us. Fortunately, we can do that very easily. Someone asked why obfuscated payloads won't run over a certain size. That's just a limitation of Cobalt Strike. And it's also a limitation of other frameworks I found. I don't know that every framework has the 1 megabyte limit, but many of them do. And I don't know if that's something I'm not actually sure why that's a limit. I'm sure it's some problem that they're all running into. Excuse me. So I'm not totally sure exactly the technical reason, but that's something that Cobalt Strike just won't let you do. So DNlib is the library that ConfuserEX is built on. And so this is another open source project that you can use without ConfuserEX. And so here is just a quick snippet. This is from a blog post that I'm going to link in a couple slides from Samuel Wong that's really great about using DNlib. Basically, what I'm doing here is I'm reading in the file name. I'm then changing the assembly.name property to be a random string. And then I'm looping through for attributes assembly title, assembly product, and GUID. And for each of those, I'm replacing them with random strings. Or if it's the GUID, I'll replace it with a brand new GUID. So once you've run this, it will output it to the original file name .obs. And you can see here at the top left, I've got the Seatbelt that I ran through ConfuserEX. And at the bottom right, I've got Seatbelt that I've ran through that code that I just showed you. And now you can see the assembly title and assembly product are totally random strings that I generated. So I could put really anything I wanted there. And then the GUID is totally different. And really, you can change any of these values you want. If you want to change the copyright or the company or the version or anything, you can do this with DNlib pretty easily. And they have decent documentation on all the properties that you can grab that way. So this sort of process that I've just shown you isn't optimal, right? First of all, we're running two different programs to obfuscate one assembly. ConfuserEX, we have to manipulate XML files in a scripted way. And this is something that when I first started Black Hills, I was writing, PowerShell scripts to read these in and modify them. And this is not something that is very fun. And it's definitely not, it's very bug prone as well. So you're going to have some issues with the XML files and things probably. And you're going to have to change obfuscation settings for different payloads. Some of them you want to use control flow obfuscation because they're smaller. Some of them you don't because they're larger. And the other problem with CEX is that it will always replace things with random, crazy long values. And the problem with this is that it actually changes the entropy, which is the overall randomness of your file, quite a bit. And I've actually heard of some security products specifically looking for a lot of random data in payloads and in memory segments. And so this is something that could potentially get you caught. I haven't experienced that, but I have heard of that being something that they're looking for. But you could consider replacing ConfuserEX with your own custom obfuscator that you could write. So I already showed you dnlib as a way to modify assembly attributes, and you can also do that to change things like method names. There's also Roslyn, which is the Microsoft compiler as code, I guess, that you can use. And for each of these, you could give them a word list, whether it's just an English word list or whatever language the company you're testing is, or you could give it a company-specific word list that uses words related to them or to the software that they already use, right? I mentioned before that blog post from Samuel Wong, and I link it here. This is a really, really great reference for writing an obfuscator with dnlib. He does a ton of the work for you. That code snippet I showed before was almost entirely copy and pasted from that blog because he provides so much to you to get started. Vic from TrustedSec also has this set of videos on YouTube where he's making a tool called Obfuscator, which is a Roslyn-based obfuscator. I don't really have much experience with Roslyn. I've looked at it in comparison to dnlib for this purpose, and I personally sort of like dnlib better. I think it's a little bit easier to use, but I think that's more of a preference thing than really an actual one being better than the other. So now that we've obfuscated our assemblies with ConfuserEX, and we've set up fork and run execution in a way that we think is going to work well, this is where we can move into operation prechecks. And what an operation precheck is, at least from how I'm using it, is basically doing everything we can to verify that our payloads are as OPSEC safe as we think. So what we want to do is test them against, whatever security products we can get our hands on before putting them in the actual environment. So in a perfect world, we'd have the exact same EDR and antivirus and all these and the same ANSI providers and know everything that they're looking for and test our payloads against those. But obviously that's not very realistic all the time. We don't always, or often at least, have access to the same security products that the environment does. I almost never do, really. And so what you can do instead, though, is you can look at the logs that those products are collecting, right? So we know they're collecting AMC, we know they're collecting ETW, and we know that they're sort of looking at memory. And so we can look at these logs and see what those log sources would provide to sort of see what the EDR is going to receive, right? Because while security products are very great, they're limited by the logs that Microsoft provides to them, right? They can only see what the operating system really lets them. So we can test our assemblies against a Defender, an AMC, and ETW to better understand what exactly these tools are seeing. So first of all, the first check that I always run is just using DNSpy. So DNSpy is a .NET assembly editor. It uses dnlib, I believe, and you just drag and drop a .NET assembly into it, and you can see the source code of the C# executable. If you drop an unobfuscated Seatbelt into it, you would see all of the method names and all these different things. When I drop the ConfuserEX obfuscated assembly that I also ran through that code snippet that I showed you, it's going to look like this, right? On the left, I have all of these totally random looking method names, and you can see how that would, of course, increase the entropy. And then on the right, I've got the randomized assembly titles and the GUID. And this is just a pre-check to make sure that it obfuscated successfully, that I remembered to run it through both tools, and that all the GUIDs and things change, right? When I was initially using ConfuserEX, this is actually how I discovered the fact that it's not going to change something like the title and the product and the GUID, because I ran through DNSpy and I noticed that the word Seatbelt was still there, and that's obviously not what I want. The next pre-check, and this is a particularly useful one, is a tool called ThreatCheck. So first of all, Defender Check came out in 2019, and this allowed you to submit a file to Defender, scan it, and then it would return the malicious bytes to you if it was detected. I think in the last year, though, Rostamouse put out a tool called ThreatCheck, which is a fork of this that actually includes the ability to scan files with AMC as well. So we're mostly interested in AMC detections because we're not writing our files to disk, but I typically scan with both because it never hurts to make sure that there are no signatures with either. So here I'm going to show you running ThreatCheck. First of all, we're going to run it against the original Seatbelt. I'll use AMC as the engine. And when I run this, you'll see it's going to find a bunch of malicious segments, and it's going to keep trying to narrow it down to find the exact bytes. I don't necessarily care what the original bytes are, or excuse me, what the malicious bytes are, but I'll show you anyway. So I can see there, okay, they're flagging on that segment. But if I run this with my confused payload, not Seatbelt, it totally gets past AMC now. And if I run it past Defender as well, it's not going to be detected by that either. So this is a good start. We've gotten past AMC and Defender, which are sort of the core sources of detecting things in Windows. And now we've gotten past that component of .NET logs, assuming that their AMC provider isn't doing anything, much better than what normally AMC is doing, which, like I said, I haven't really experienced. So the next pre-check we can do is looking at ETW logs. FuzzySec, when he worked at FireEye, put out a tool called SilkETW. And this is a really, really convenient tool for interacting with ETW at all, because it sort of abstracts away all the complexities of writing something that can collect ETW logs. So we can use SilkETW to filter for only Microsoft Windows.NET runtime logs, and we can just collect all of the data that the security provider will see. And so you can do a lot with this. We're going to do in the demo here, we're just going to search for the string seatbelt, make sure it's not in there. But you could look for any sets of data you want. You can actually write YARA rules for SilkETW, and they provide a YARA rule for seatbelt that, of course, our confused binary would get passed as well. But you could write YARA rules that include any strings you want to make sure that they're getting passed, ETW, well, not getting passed, but that they're not sending logs to ETW that you wouldn't want them to. So here I've got this demo. So SilkETW is great because they have a GitHub release as well. So you just download the binary basically, but it will start collecting. I will then run not seatbelt with OS info, and I'll go and stop the collector. You can see there were hundreds of logs just in that couple of seconds. And if I open this seatbelt.txt that it generated, you can kind of see what these look like. And if I search for seatbelt, it's not in there. So obviously you could do more searching than just for the string seatbelt. This is just for the simple example, but this is a really nice pre-check because it helps you verify that there aren't method names that aren't being obfuscated, right? You could click through DNSpy all day, but that's really hard to automate. And so instead what you can do is write YARA rules for specific things that you're concerned with and sort of run them through SilkETW and see if they're being detected that way. All right, so the last pre-check that I want to talk about is Elastic Endpoint. So a couple months ago, John Strand had a talk on open source and free EDR options. And that sort of piqued my interest because, like I said, I can't test it against all the expensive EDR products that clients might have, but I can test it against free EDR. So I went and downloaded all of the EDR options that he talks about. And what I found to be the most difficult to bypass was Elastic Endpoint. Theoretically, you could test your payload against all of them, but Elastic Endpoint to me seems like the strongest choice. And so I figured just bypassing that is an easy way to do it. And so this is totally free, and you can deploy it really easily. I'm actually going to show you a video here in a second that is me deploying this from scratch because it's so quick. It's not an optimal setup. It's not great, but having just enough to test payloads is really easy to set up. And you could use this to test initial payloads or really any post-ex capability because it's really meant to be an EDR. And so, and luckily, this EDR will work totally offline. You don't have to give it internet, so it won't submit any payloads. So it's actually a really good option for testing things in this way. So here I've got this Ubuntu VM where I've cloned that Docker Elk repo that I linked, which is just a way to set up Elasticsearch with Docker. I have to add that last line to the file to enable API keys for authentication. And then I will run Docker Compose up. It's going to spit out a bunch of information about the Elasticsearch and Kibana and Logstash settings. I'll go to my Windows VM where I want to run the payload, and I can see that the Elastic Stack is up. So I'll go ahead and download Elastic Agent, which is sort of an endpoint management tool. I'm then going to log into the Elastic interface. There's a couple loading spots where it's going to be a little slow. Sorry about that. So I'm going to go to the security page. From here, I will go to, I believe, agents or add data with Elastic Agent. And so what's nice about this is like I said, you don't need internet access. You don't need anything once you've set it up. So you can set all this up. You can configure it to pop up alerts on the desktop so you know if it was successful or if it was caught by Elastic or not. And you could probably automate a lot of this, what I'm doing right now. Obviously, I am sort of clicking through this manually, but I'm sure you could automate this part of the setup as well. So you can see me here waiting for a second. I'm also running this on systems with very low resources. I think the Linux VM has like 2 or 4 gigs of RAM and 1 CPU, and the Windows VM has 4 gigs of RAM and 1 or 2 CPUs. Like it's very minimal. So I've got to grab this command to set up. I've got to replace the IP from localhost to be the IP of the Elastic Stack server. But then I'll copy this and I'll go into PowerShell and I can run this and it will install Elastic Agent for me. And they have instructions online on how to do this. So if you don't catch it here, you can either watch the recording or you can read their instructions, but it's really not too challenging to get set up. So once the Elastic Agent's been installed, if I come back into this dashboard, if I go back to integrations, here's where I can install Elastic Security, or excuse me, endpoints. I guess it's Elastic Endpoint is what it's called, or Endpoint Security is the name of the integration. It's kind of confusing. So I'll choose my default policy. I'll call this EDR. I'll go ahead and save it. I will then deploy the changes, and that will load for a second. Somebody asked, how do you configure your system? Well, that's a good question. I'll answer the Defender real-time monitoring in a second. So if just to show you what sort of EDR configuration looks like, you can see if I go to edit integration here, the default is to prevent any malware, to notify the user, and then to just protect against anything that they can possibly protect against. The only thing that's disabled is register antivirus, and I leave that disabled because that will actually cause it to replace a Defender, and I don't want that for my test. So if I refresh services now, there's 2 new services, Elastic Endpoint and Elastic Agent are both running, and so I've got that totally configured. So if I jump over to this next demo, here's where I've got, this is the same host with the Elastic Agent and Endpoint installed. I've got real-time protection and cloud deliver protection enabled. So to answer that question, I always leave real-time protection and cloud deliver protection enabled, but I disable auto sample submission. And typically what I'll do is I will totally update the machine, and then I will take it offline and run payloads in it, and then reset it to a snapshot of right before I ran the payload, so that way they can't submit any data. If I'm less worried, such as if I'm just running public PostEx tools, I might run it with the internet enabled so that I can use the cloud deliver protection, because that does have some improvement sometimes. What I'll typically do is I'll have one directory that is excluded from Defender that I can drop all my payloads to, and use that as sort of a place to run at least initial payloads from, or at least put them there and then copy them to where I want them to get detected from to see if they get passed right. As far as post-exploitation goes, the Cobalt Strike instance that you see is actually not in this VM. It's a little bit misleading from this demo. It's not in the VM. It's sort of above the VM. And the payloads that I'm giving it are not in the VM at all. And so there's no reason for me to disable a Defender or to disable real-time monitoring or any of these things for this setup. So I'll go ahead and run this. And just to show you, I'll just use execute assembly. I'm going to give it my not seatbelt.exe that I obfuscated and changed earlier. I'll pass it the quiet option so it doesn't print the banner, and then I'll run osinfo. And oh geez, we're getting close to the time here. Well, this is my last big thing. So, all right, so that's seatbelt running with all the protections enabled. So with that, I would feel pretty confident moving forward. Some closing thoughts on endpoint execution is still very commonly used, right? Someone asked if execute assembly was still usable or if they had to use something else. Execute assembly still works great. I just used it there with that EDR. I just used it on a red team just recently. It's something that is very successful and can get past detections in modern environments. Fork and run is difficult to detect, right? If you take all the precautions. If you use the default settings, it's not difficult to detect because there are lots of signatures for the default configurations. One thing I didn't talk about today was proxied execution, which is sort of using something like in-packet scripts over SOX proxy. And that does have some benefits and some cons as well. And so that's something to consider, but not necessarily something that is always better or always worse. But yeah, with that, that's pretty much my talk for today. I've got my sort of shameless plug here at the end, where if you enjoyed this, I've got a class coming up in August that is totally virtual and then a hybrid at Deadwood. They're both 16-hour classes where we cover enumeration, persistence, privilege escalation, and lateral movement. For each of these, we're going to talk about several different techniques. We'll talk about what rules exist to detect them. Got a discussion for each on what the implications are, what artifacts they'll leave. And then we'll also use some different open source tools, and we'll also write our own implementations of certain capabilities by sort of taking examples from online and writing things from scratch in C#. So with that, thank you guys.
Holy cow, Kyle. Whew. That was
Right
a lot
up
of
to the time.
information in that hour. Wow, that was awesome. One person was impressed that you were able to do all the demos while drinking water, but they were recordings. So.
I got 3 hands, I guess. Yeah, they were all
right,
recorded.
so what we're going to do right now is we're in overtime. So if you need to go, feel free to leave. Thank you so much for being here. Kyle already gave his closing thoughts, and we appreciate you joining us today for this Black Hills Information Security webcast. If you ever need a red team, threat hunt, pen test, anything like that, you know where to find us. But Kyle, what we're going to do is we'll see if there's any questions that come in based on all this information. I think people are still processing and downloading and trying to go through. There was a lot of links. There's a lot of tools. There's a lot of things. And so those were captured throughout, and we try to drop them into GoToWebinar as best we can. But let's see if we have any questions that are coming from the audience. A lot of people said thank you. So thank you for the training. I think someone asked, is the training based on Cobalt Strike? Yeah, is it based on Cobalt Strike as the command and control?
The training is not based on Cobalt Strike. So I'd love for it to be, but I can't get everyone licenses for Cobalt Strike. And so the first run, we use Sliver, which is an open source C2. But this next run, I've been sort of rewriting it to use Mythic, which is a command and control framework from SpectreOps that I'm a huge fan of, actually. And I'm honestly moving towards it as sort of maybe even replacing Cobalt Strike in my sort of day-to-day. So it's definitely something that I'm excited about using for the class, and I think you'll probably enjoy it if you end up taking it.
Yep. Someone said that, thank you for the training. They have to jump on other training. And then someone said, one of the best BHIS presentations I've seen. So,
oh, awesome.
Yeah. So that way, when you fall asleep tonight, you just remember that one. You're like,
yeah. That's all I'm thinking about.
It doesn't matter if I have a low Uber rider rating. Just is the recording is the recording of the session will be shared. Yeah, so we always send out an email after the event. So 24 hours from now, you'll get an email saying, thank you so much for joining us. And in that email, we'll have a link to the raw recording today. And then about a month or a month and a half from now, we'll have the recording that's been edited and processed. That will be available on our YouTube channel. So we're getting caught up. We had a lot of content that we created this year, and there's one person editing it, and he's listening in right now going, I know, I'm gonna get caught up. Let's see. Anything else? For everyone that signed up for the zine during the webcast, thank you so much for signing up for that. If you don't know what a zine is, it is a self-published magazine that we're creating in Infosec. There's going to be puzzles, coloring contest, articles, lots of things in there. So we're having a lot of fun with it. So Kyle, I'm looking for questions. I'm not seeing anything.
Yeah, I'm watching live chat as well now. Nothing popping up.
Here we
go. You missed your question. Oh, I see one.
Here's one. What is the last C2 framework referenced?
The last one? Oh, Mythic.
Okay, so Mythic.
Here, I can give a link to that.
And then someone said, really neat, you said fork and run might be sufficient. Can you give some primers on how to set it up more OPSEC safe? Yeah.
So if you go back in that second section of my presentation where I talked about those Cobalt Strike options, those are all options that affect fork and run execution and should make the reflective DLL portion of that more safe. On top of that, you just include some sort of plausible child process execution, and then you look at those things together should make the fork and run execution pretty safe. Again, you can test it against something like Elastic EDR, and then you just have to worry about the .NET logs.
Okay. Question, what are your thoughts on detecting bypasses loaded using .NET reflection?
Detecting bypasses loaded using .NET reflection. So any bypass of AMC or ETW is still going to have the same effect on something like AMC.dll, right? You're still going to be, unless you're using a bypass that I'm not familiar with that doesn't patch AMC, you're going to be modifying that DLL in memory. And so it can still be detected in the same way where EDR can look at AMC on disk and can look at the AMC in each process and compare them. And if the hash isn't the same, then they know it's been modified and they know that someone is tampering with AMC. So I can't say for sure that wouldn't work because you might be referencing something that doesn't patch AMC.dll, but if so, I think it's still going to get caught the same way.
Okay. In a red team engagement, how would you expect the deployed AV EDR for the testing phase?
So I typically try and expect the most secure environment that I can imagine, right? I'm imagining the absolute best EDRs that I've gone up against. I'm imagining, very strong antivirus with very strong policies and a full blue team that's looking at all the logs and anything that I can basically imagine in terms of detections, right? And I'm sort of trying to gear what I do towards that. So I'll check it past all of the tools that I showed you, make sure that it gets past all of those at a minimum. And that way I know that the logs that are being created are, the fewest possible. And so if they do detect them, props to them. But at that point, there's not much more I can do. If I've sufficiently obfuscated my payload to the point where it is totally unique looking and has very few indicators in terms of AMC detections or known ETW strings, right? That's about as good as I can sort of plan to do. I combine that with something like Elastic Agent, or excuse me, Elastic Endpoint, to make sure there's nothing I missed. But after that, I'm sort of assuming that whatever I've made is going to be sufficient. And so far, it's worked pretty well. I haven't had too many issues with the fork and run execution in the tests that I've done.
Kyle, if you look in the private chat, I think there's some clarity for the question itself.
Oh, I see. I see. Okay, so you're loading a system reflection assembly load file that isn't AMC aware. That's a good question, actually. I haven't really played with that too much. I'm sorry, I totally misunderstood your question. Honestly, that might work. Again, the thing with AMC is that you can bypass it with sufficient obfuscation, which is something you'd want for ETW anyway. And so if you're going to be obfuscating for ETW, you might as well submit it through any channel you want that may or may not get scanned by AMC, because it wouldn't hurt to get past AMC, but it also may, again, I'm not familiar with this method in particular, but it might generate additional indicators that assembly.load would not. I don't know. Can most spy passes also be used for stagers, launchers, beacons? That's a good question. So yeah, so today's talk was all about post-exploitation capabilities, what to do once your Cobalt Strike or whatever else beacon is running. If you're writing your initial payloads in .NET, you could absolutely use any of the same obfuscation and detection methods to look at them. Obviously, the fork and run discussion doesn't necessarily apply in that case, but yeah, all the same. I'm using ConfuserEX and using SilkETW and ThreatCheck to scan them is obviously a good idea for all those as well, yeah.
All right. And then let's see, is there anything else? Do you have any recommendations to learn a lot more about Cobalt Strike? I do have access to a Cobalt Strike license, got my first OP4 engagement next week.
Awesome, yeah. So there's actually a really great video series from Raphael Mudge, who's the creator of Cobalt Strike. I think it's 9 parts or 12 parts or something, but it's really great because he goes through from every part of your engagement, how to use Cobalt Strike the best way you can. And he covers a lot of the features that I talked about, such as the fork and run configuration. He talks about PPID spoofing for fork and run. He also talks about setting up redirectors and setting up your listeners and pretty much anything you would need to use Cobalt Strike. So I highly recommend those videos.
Right,
is block DLL still relevant? That's a really good question, actually. I personally avoid block DLL very heavily. So block DLL, if you're not familiar, is a command in Cobalt Strike, but it's also just sort of a term used to refer to a general technique where you set a process attribute that only allows Microsoft signed DLLs to be signed. And there was a very short window where this was extremely useful because none of the security product or EDR vendors were signed, and you could do this, and none of them could inject into your process and monitor it. And this is particularly useful for using unmanaged API calls, right, that usually have user mode hooking, because now there is no user mode hooking if you block their DLL. Now, after that, though, security vendors quickly realized this, and they went and got Microsoft signatures. And so most of the big vendors have Microsoft signed DLLs now, and so they will see it, and they'll see that that attribute is set, which is not something that every process has, and it certainly isn't something that, most processes, if you load them and they don't typically have block DLLs enabled, and it's enabled, that's going to be pretty suspicious and a pretty obvious indicator. And it's really not going to do much good most of the time. So I typically don't use that. Can you elaborate on how to get rid of the title and other stuff that are not obfuscated by ConfuserEX? Yeah, let me go back to that slide, actually. Okay, so dnlib is the underlying library used by ConfuserEX. And what dnlib lets you do is read an assembly and sort of modify specific attributes of that built.NET assembly. So this is a small snippet of code where I'm importing dnlib in sort of the cropped out portion of this. And then this first line, I'm reading the path of the .NET assembly. I'm then loading it with dnlib. And the first thing that I'm doing here is I'm setting assembly.name to a random string. So random string is a method I wrote that just returns a random string. So assembly.name is set to a random string. Then I'm looping through each of these attributes. So assembly title, assembly product, and GUID attribute. And for each of these, I'm setting, if the name is GUID attribute, I will generate a random GUID, which is another method that I wrote that just outputs a new GUID from a new GUID to replace that one. And then if it's not GUID attribute, so if it's one of these first two items, it will replace it with a random string. So once I've looped through all of the attributes and replaced all three of these, I then write that modified assembly to the original file name .obs for obfuscated. So essentially what I'm doing here is I'm going through each of the attributes and I'm looking for assembly title, assembly product, and GUID. And if I find those, I'm changing them.
All right, I think we'll do one more and then we'll be out for today because I'm guessing you're exhausted from all the talking.
Yeah.
I'm looking right now. I was going to have us play competitive versions of backdoors and breaches, but we'll just save
You just didn't want to lose.
Do you want to play?
I'm sure I would lose. I played almost one game, if anyone's wondering.
You were doing pretty good. I rolled that one and lost my whole kill chain. So, all right, everybody, thank you so much for joining us today for this Black Hills Information Security webcast. You know, we do this all the time. So if you were new here today and you're like, you do this all the time? Yeah, we do it all the time. Just like we have a 4-hour workshop coming up with hands-on labs. It is complicated to pull off a free workshop with hands-on labs with thousands of people, but we love doing it because that's how we got started last year. And during COVID and everything else, we're like, oh, let's teach people, let's give away with free workshops. And then it's turned into something really cool. Kyle, thank you so much. If you ever see Kyle in an Uber, he's ever in your Uber, please give him a 5-star rating.
5-star.
Please.
I need
it.
He needs it bad. All right, everybody, we'll see you next time. I am ending the webinar for all. Bye-bye.